Okay, hello everyone. Yeah, checking the quality of the sound. Want to see if everything is right. Yeah, looks like microphone is running good. Everything seems to be okay for now. Quality of the sound as well seems to be good. Nice. So we just started the stream. We'll continue our session on solving LeetCode problems. And today we'll start with solving the problem of the day, which is a minimum number of steps to make two strings anagram. The problem in itself, it's not too difficult. As we can see in the stats here, acceptance rate is 80%. So this can be considered an easy problem as well. So anyway, let's start solving it and see where we'll get. I'll have a sip of coffee and we'll continue. So for this problem, I think easiest will be to have my setup in VS Code, because I'll add the unit tests and then it will be easier to go from there. Yeah, let me copy this. Don't know what's going on. Something is weird. I cannot. Yeah, with the name of the problem, I cannot copy it. Okay, but I don't really need it for now. Okay, good. So what's the problem called? Minimum number of steps to make two strings anagram. Okay, so let's add it. Pub mod minimum number of steps to make two strings anagram. We added this. Let's see it. Then we'll need to copy the interface. For this, we'll have a pub struct solution, which we'll not need to copy it when we'll send the solution back to LeetCode. But for now, let's see. So we have this. Usually I like to mark with a to-do for this to compile. And then let's add our mod with tests. We'll use things from above, everything. And I'd like to create my first test called test solution. Okay. So this is what I like to do for this kind of test. Yeah, we'll need to mark this as a test to be able to compile it. And next stage, I have a snippet to create scenarios. So for this scenario, we'll have something on the following lines. We'll need a tuple with two strings. So it will be like to string one. For now, I don't need specifically to write what the strings are, because I just define them. And then let's say a one, and then we'll have like solution here and min steps. But input in our case will be a tuple in itself. So we'll need to destructure it. We can call s and t as in definition. So here we'll put S and T. We'll have the result. So we should be good. This compiles. Yeah, I will not need to do that. This compiles, but it will not run because we have a to-do. And a lot of warnings as well. But for now, we're good. Next stage, which I like to do, it's to add our test cases, our specific test cases. So let's check here. So we have 3 examples. Let me copy this to have it pasted as a comment here, and we'll be able to add faster our examples. So let's say for example number 1, we have BAB and ABA. The anagram tells us that the result should be 1. Okay, so we added this. Let's add another. For example number 2 will be LeetCode. And the second will be practice. Expected result is 5. Moving on, we have anagram and Mengia. And expected result will be 0. Okay, so these are our test cases. Probably we should start thinking on how we can solve it. So for now, we don't need the examples. Replace P, R, I, and C from T with proper characters to make it anagram of S. One thing which I like to do when solving this kind of problems, it's to check hints. So hints are very useful. Often by just looking at a hint, they'll suggest exactly what will be the solution to our problem. And what they suggest at first is to count the frequency of characters of each string. And then we'll need to loop over all characters. If the frequency of a character in T is less than the frequency of the same character in S, then add the difference between the frequencies to the answer. So pretty much they gave us the algorithm. So what we'll need to do is just to code it. So let's start coding. So first step, let's try to count the frequency of the characters of the strings. Maybe I'll create a simple function, call it frequency. So we'll return a hash map of char and usize. This will be the count. Then we'll provide here the string. Probably we'll do an str because I don't like to consume the strings. This creates issues in the long run, so we'll need to clone it if you want to do any other operation. So for now, we'll just use this. So we can call it char frequency. Maybe that will be more specific, but should be good. So in order to add the code, we will we'll get the chars, and then we will fold it. So we'll have a hash map new, and here we'll have a mutable accumulator and the char itself. So the char, I don't know if that's right type. Yeah, indeed it's char. We'll return the accumulator, and here we'll do accumulator.entry gh or insert 0 let n entry, and we'll do entry as dereference plus equal 1. So that will be the code to count the char frequency. So yeah, you can remember this part because this is super useful, used almost everywhere. Yeah, let me remove this. I don't like too much noise. So yeah, let's have two variables now. Frequency 1, let's call it like that, and we'll do like char frequency of s. And we'll do the second will be frequency 2, and will be like char frequency of t. So we'll have two hash maps. Now, kind of what we'll want to do, it's to try to group them together by letters. And the simplest way how I see for this to be coded can be something like this. So we have like frequency 1. We'll do like entries, or not entries, or entries, I think. Values, not values. I need both entries. Yeah, let's try. I kind of forgot hash map, so I'm pretty sure it has entries. Debug map entries. It does has entries, which is a key value pair. I don't understand why I do not see it here. Okay, so let's write it. Entries. Let's try like that for why this doesn't work. How yeah, this is a little bit weird. I don't understand why we don't have entries. But what's the not Copilot, I want a browser. Okay. Yeah, let me search this. Looks like simple browser has troubles to parse stuff. It doesn't want to open it. Okay, let's have a new window here. Google. Yeah, let me zoom it for you. Hash map entries in Rust. Entry. Entry or into values, into keys, iterator, from, so it's just an iterator. So just iterator gives us the right result. Okay, let me get back then to, so this stuff automatically will iterate them. Okay, so that's good. Actually, that's fine. So what we need to do now, we'll do like a frequency 1, and then iterator, not inter, but iterator. We need to iterate it. And then we'll add a mapper function where we'll have like our tuple here, which will be gh and count. Gh and count. Yeah, but this is inside a tuple. So we have our mapper. And now what we'll need to return, it's two values, one from left and right. So we'll have the so we'll need to get the value from the other map. So the value from the other map will be, I assume it's the default will be 0. So let val will be frequency 2 get gh or default unwrap or unwrap or 0, as we want the usize to be the right one. And now we'll do the count and the val. This will return our mapper. Yeah, here we kind of will need to do a reference, as everything is a reference here. So we have two references. Maybe we can dereference both of them to use it easier. Okay. So yeah, at this stage we have our iterator. Next thing which we'll need to do, so we have pairs. So our pairs will be in the form of for A, for example, we'll have like 4 and 2. For B, we'll have like yo, hey now. hello, how are you? Yeah. Oh, awesome. Yeah. Hello. I'm good, thanks. Cool. So did you manage to solve the last problem? I think you wanted to try it in Python, if I recall correctly. Oh, awesome. Yeah, nice. Yeah, today's problem, it's a medium one, and it's quite straightforward. It is a little bit of work to be done, for sure, but it's nothing super difficult and fancy. So you'll need to have like 2 hash maps and try to count the letters left and right, and this will be pretty much the result. So what I want to do, even I don't think we need this. So maybe what we'll need to do actually will be something like yeah, cool. Nice. Yeah, binary search, it's a pretty cool algorithm. And today's and this week's problems, I think mostly of them were on binary trees. It's not exactly the same thing as binary trees and binary search, but the next stage, I guess, after binary search is for you to look into binary trees and do like DFS, depth first search, or breadth first search. That will be a cool thing for you to look into. Yeah, if you need to go, yeah, wish you a nice evening. Have a nice day. Yeah, thank you for popping in. Uh, yeah, cool, cool. So yeah, let's do the difference. So what will be the difference? I guess first or second maybe, or we'll do absolute values. Yeah, maybe we should do absolute values. So I'll have like a val minus count. ABS. Do we need to do it like this? Probably. And then we can sum it. What's the trouble with ABS? Yeah, kind of ABS will not work for use sizes. So we'll need to do as I32s. And then we'll need to do structure like that. Yeah, bye-bye. Yeah, thank you. Thank you. Yeah, I'll try today to solve a couple of problems as well and explaining them. I see people watch it. So I hope to be useful. So we'll do like I32, but actually we don't need to do it like that. So pretty much that's it. I think this should work. Let's see. No, it did not. Let's check why. Left, it's 2. Right, it's 1. And let's check why. Let's go with the debugger. So we got count 1 and val 2. Yeah, this okay, so val minus count will be 1, absolute value will be 1. Okay. Next one will be B. Which we have 2 in first and 1 in second. Yeah, looks like it's not this algorithm. I'll need to do something else here. So just doing it in this form doesn't help much. Because in the first we have like two B's and one A. Two B's and one A. And the second we have two A's and one B. So we've got the frequencies. So we should be pretty close. Yeah, let's get to our drawing board. Maybe there we'll come up with a solution. So we've got F1 or the frequency 1, which will have A. For first we'll have 2 and B 1. For frequency 2, we have B in this case will be 2 and A 1. So our goal is to make these two equal. And how can we do it that? How can we do that? Yeah, that's a little bit interesting. How did I get 1? Because actually it's a 2 operation, or it's not operation. Yeah, let's check again. What do they want from us? Because maybe I didn't read it correctly. An anagram of a string is a string that contains the same characters with a different or the same ordering. Okay. Oh, so if we change, in our case, if we change here A to BB, so yeah, actually, yeah, in this specific case, what we'll need to do, it's like removing 1 from here and adding that one to B. So plus 1. And that will make it equal in this case. But if we do it in the following lines, so we'll have like A. For A's, we'll have the 1 part, and for B, we'll have the 1 part. What this stuff gives us? Not sure. Only this example doesn't help much. Let's try to pick another one. So let's check probably anagram. Anagram and manga. Yeah, so we'll have this. Anagram. And second will be manga. So if we do the frequencies of A, will be like 1, 2, 3. N will be 1. G will be 1. R will be 1. And M will be 1. So on the right side, we'll have the following, like A, 3, and 1, G, 1, M, 1, and on, this will be N, and R, 1 as well. So they are equal. So the sum in this case will be 0. So the sum in this case will be 0. If we go with the third example, LeetCode and practice. Yeah, let's check this one. So let me use another color. So LeetCode and practice. So we'll do like this. L, we have 1. E, we'll have like 3. T, 1. C, 1. O, 1. And G, 1. And if you do the right side, P, 1. R, practice, 1. A, 1. C, 2. T, 1. I, 1. And E, 1. So here, the single common denominator, or not denominator, but equal part will be like T. For L, practice T. What's that? That's C. C1. No. T I. Yeah, it's I. Practice. So we have T common, and then we have 5 other letters which are different. So if we try to do my ABS algorithm, will be like 1 minus 0, because we don't have L for L. And then for E, we have 3 minus 1. This will be for E. For T, we'll have 0. It will be 1 minus 1 for T. For C, C. We have actually C on the right side, so it will be like 1 minus 2. But we go absolute value, so it will be like 2 minus 1. We don't mind it. This will be like C. For O, we don't have O, will be 1 minus 0. For D, we don't have D, this will be O. D 1 minus 0. And we have a bunch of them remaining on the right side. So probably what we should do, actually, it's get the values from the right side, not from the left side. Because we want to make this one. So what we try to do, this one to make it equal to this one, not vice versa. So I shouldn't count from LeetCode to practice, but vice versa. Practice to LeetCode to see what stuff is there. And if we go like that, P will be 1 minus 0, because we don't have anything. R will be 1 minus 0 in this case. A, as well, we don't have 1 minus 0. C, we do have one C here. So it will be 2 minus 1. For T, we have 1 minus 1, because we have E as well. We don't have. And I and E, we have 1 minus 3 here. Actually, we have 2 remaining. So this means we need 1, 1, 1, 1 again, 0, 1, and this we have too many, so we don't care about them. So this will be as well 0, I guess. So if we sum all the things we need to make A into B, this will be 5, or our result. But is it possible though? Is there a way where we need to put like minus 1? So no, they have the same length, so it's not possible. So the strings are on the same length. I guess, yeah. We should do a little bit of clean up in our code. Because here we'll not start with frequency 1. We don't need the frequency 1. We'll need a frequency 2 here. So we'll start with the frequency 2. and then we'll search the value in frequency 1. Yeah, let me rename them because this is confusing. So frequency 2 count, and I call this frequency 1 count. And here we'll do our logic. Let result will be frequency 2 minus frequency 1. We'll do these two counts. Yeah, we'll still need it to be an I32 because we cannot have a negative number, so let's cast them as I32s. But actually, maybe I can do that even at higher level. Maybe I can do that here. Now I'll not need to do this casting. So if this is positive, we'll return a result. If it's negative, this means everything is good, and we'll return 0. And then we sum it, and we should get our result. Cool, so this works. We have all of our examples. Oh, hello, Zeke. I saw your message. I want to master JavaScript. Yeah, I do use JavaScript at work, but this streams, it's more of using Rust. I'm not sure if I should suggest you to start with Rust first over JavaScript. It's up to you. I started with PHP and then moved to JavaScript. So Node.js on the backend. So at my current job, I'm a backend developer using Node.js with TypeScript. So with TypeScript, it's pretty solid language. Without TypeScript, it has its benefits, but also its troubles. In order to master JavaScript, I suggest you a couple of very good books. So you can try to find them. It's called You Don't Know JavaScript. I think they are online. So you can read them. I mean, these are by far the best books on JavaScript ever written. Once you start digging into each one of them, it's your mind will be blown because a lot of explanation why things happen, why they happen. So I think somewhere should be the first edition. I think this is the second edition, and at first it was like 6 books or something. Scope and closures. Okay. Just a moment. Yeah, so you can start here. Let me, I guess, how can I send it? Maybe I send it in, yeah, it's a bit ugly because I use I use the laptop. Yeah, I guess you write in the browser, you don't know JavaScript, you don't know JS, and you'll get to see these books. Okay. Start by reading them. So getting started, you can read it in GitHub. So tokenizing, parsing, code generation, You'll have like a lot of interesting things on why JavaScript works the way it does. So yeah, they are online. You can buy them. So, but they are by far the best books in JavaScript. If you want to master them, to master JavaScript, I suggest to start here. Okay, yeah, let's get back to our problem in Rust. Yeah, we are done with the problem. As you can see here, all our test cases work fine. One thing which we can do, I try to run cargo Clippy, and it will give me suggestions on how I can improve my code. So I see a lot of suggestions here. Yeah, but I'm not sure if all of them are for this part of the application. Maybe I can run, let me see. Cargo Clippy, can I specify the file? And the file, I want to be minimum numbers of this. Cargo check. Yeah, it doesn't work. Doesn't work like that. Yeah, so probably in the future we'll do a separate project for us to have Clippy as a helper. Yeah, let's copy this and run it in LeetCode and see where do we stand. Yeah, we don't need to do this. Let's run first and make sure this works. Yeah, this works, and let's submit and see if this will be accepted. Cool, it's accepted. And I have a streak of 18 days. So 18 days I solve problems. Want to keep it going and see how far I can go. So another thing, once you solve the problem, as you can see here, we have like 21 millisecond and a lot of memory, is to analyze a little bit the code. So let's check what will be the time and space complexity of our code. So for time, what actually we're doing is first is going through all the numbers one time and storing or counting the frequencies. And then we do a second run to check the frequencies if they are satisfied or not. So I guess this will be O of 1, O of n, or a big O of n. It's linear. So linear is considered a pretty fast algorithm. Though on space, we use kind of a lot of space because we have extra 2 hash maps or 2 dictionaries, and it will be like O of 2n. Here it will be as well like 2n, but we don't, for asymptotic notation, or we just ignore the constant, and we'll have like O of n for space and O of n for time. So it's pretty fast algorithm anyway, but as you can see here, it's not the fastest. So let's see other solutions and compare with what we did. So these guys, what does it do? So instead of using a dictionary, it uses an array of a vector of size 26, and then do the frequency by counting the bytes. Does some unsafe code. I mean, this is a micro optimization. For sure, this should be faster. And then we have like a C1 and C2. He zipped them and does the same thing. I mean, yeah, what does he do? It's exactly the same algorithm, but it's uses an optimization. Instead of using a hash map, which uses a lot of memory, he uses a vector. And this will be faster because for hash map, actually we'll use two vectors. One for the keys, which will be the chars, and the second one will be for the values, for the counts. But in this case, we don't care about, because we know the letters in English start from 0, which will be A, and 26, 1, which will be Z. So he reduces the memory by using only one vector with the counts. And in our case, it will be like 2, 2. Does the zipping, does the sum. So it's the same thing, but a little bit more optimized. So it's a cool trick. It's good as well to check other solutions and try to understand what did he do and use as an approach. Cool, so we solved the problem. Yeah, let's get back to our easy problems, because that one was a little bit more difficult. Let's tell it like that. But we have our easy problem going. So we have 64 out of 761. We got our filter, so we'll use easy, and we need to sort by acceptance in descending order. I think we go one by one. So we are 46 minutes up. I think maximum number of words found in sentences. I think we stopped here. So yeah, let's get to this one. What's this problem about? Given an integer number n, return the difference between the product of its digits and the sum of its digits. Okay, so what we need to do here is transform this. Instead of having it in this form, probably it's easier to have it as a string. So if you want to transform it, so my idea is to transform it as a string. So let's assume we have like 2, 3, 4 as a string, and then we can easily have it as a vec of chars. We can do it this way, or we can try to get the values by dividing. Now, I guess it's the easiest will be to have it as strings. So let's do it like n to string. Then we have chars. Maybe we will. Then we'll do a map. We'll have x. I think it's 2-digit. And we need to parse, set the radix. I think something like that should work. Okay. Maybe we'll collect it. Let's collect as the vec of 532s. Let nums, and then we'll do like nums iterator fold let product will be fold. So this will be like multiplication of all of them. So for product we'll do 1, have accumulator and item, and we'll do accumulator multiply by item. This will be for product, and for sum nums iterator fold 0, same thing, and class equal 1. And we do prod minus sum. Yes, this should be it. Yeah, let's try to see if this compiles. It does not. Why? Oh, because this flatten. We need to flatten it. Because okay, can build from of elements of U32. So why this is U32 as I32 I want? Okay, unwrap it. Let's unwrap it as I32, and then we'll not need the flattened part. Found tuple. Yeah, fortunately this doesn't work, so we'll need to do it like that. Y multiplied by 1. We don't need to multiply by 1, but so it needs to be like this. Okay, kind of borrow as mutable. And we need to do it mutable for both. Awesome. So we have 2 tests successful. Let's submit and see if this will work. Indeed it does. Let's see what will be the other solution. Yeah, this is actually the other approach which I was thinking on going. It's to do like not as a string and then pass char by char, but to have this modulo 10. So this logic will be to get the values of each number. So when I started coding like 15 or 20 years ago, I don't even recall. So yeah, I have 15 years. Yeah, like 17 something years ago, when I was in the 9th degree. So I used to code it in Pascal. So I did things like that. So this approach, it's faster and uses less memory for sure than this one. Because this does a lot of manipulation. We transform it into string and then we pass it back to digits. So this algorithm is way faster. And I suggest to code it like that. But I guess for now it doesn't really matter. It's good enough. We can get back and continue with the next problem. Okay, so the next problem. You are given a positive integer num consisting of exactly 4 digits. Split num into 2 new integers, new1 and new2, by using the digits found in num. Leading zeros are allowed in new1 and new2, and all the digits found in num must be used. So for example, given num 29, 32, you have the following digits: 2 2s, 1 9, and 1 3. Some of the possible pairs new1, new2 are 22, 93, 23, 92, 2 2 3 9, and 2 3 2 9. The minimum possible sum of new1 and new2 Okay. Yeah, that's an interesting one. So let's see. Hence, notice that the most optimal way to obtain minimum possible sum using 4 digits is by summing up 2-digit numbers. Yeah, that's logical. We can use two smallest digits out of the 4 as the digits found in the 10th place respectively. Similarly, we use the final two larger digits as the digits found in one place. Topics. Greedy, sorting. Oh, so it's exactly 4 digits. So we don't need to think. So let's see the constraints. So from 1000 to 9999. Because these kind of problems with minimum sum of 4-digit numbers after splitting digits have a flavor of dynamic programming. So I thought we should use like some dynamic programming approach into solving it. And maybe actually we should try to use some dynamic programming approach. But a greedy solution here as well works. But I'm not sure I really understood what exactly. So let's read it once again. Must be used. For example, given num 29, 32, you have two 2s, one 9, and one 3. Some of the possible pairs, new1, new2, are 22, 93, 23, 92, 2 to 3, 9, and 2, 3, 2, 9. But why can we can't have... Oh, so we need to do the minimum, not the maximum. Split num in two new integers, new1 and new2, by using the digits found in num. Leading zeros are allowed in new1 and new2, and all the digits found in num must be used. I don't understand why we don't have an example with the 9 being the first. So yeah, let's use our drawing board for this example and try to understand what exactly is going on, because I have some trouble understanding. Probably it's an easy problem, very likely. Yeah, that should be good enough. So we have the following. So we have like 2, 2, 3, 9. How did we get only some possible pairs, new1, new2, are 29, 23? So we do this. Okay, that's one pair. So let me write it down, 29, 23. What else? But if you do all combinations, it will be like something like that. 22, 39. This will be 1. 23, 29 will be 2. 29, 23. Oh, so this actually are the same, some wise, so we don't care. We'll not need to sum it. What else? But wait a second. How to put this? So if we go this approach, we know for sure that this will be always the right answer. Because if we put them in order, all the time the minimum will be here, and the maximum, we'll have minimum plus the maximum, and this will be in between. So we'll get always the right value. So yeah, let's check another example. So 40009. So this one. 4009. If we sort it, will be something like 0049. And we'll do like that. So it will be like 09 plus 04. And expected result will be 13. Is that correct? Yeah, it's 13. We can see it here. Specifically for this case, we'll do like yeah. Here, actually, we can use the approach from the previous one to get the values. And store it into a vector, and then sort the vector, and then use the values. So how can we do that? We can do in the following manner. So we'll have like a vec, we'll have a mutable vector. Can I do it some way to not use a sorting algorithm? Because anyway, we kind of need to use a sorting algorithm here, but I don't know. So while temp greater or equal than 0, greater than 0, let's put it this way. Vec.push num modulo 10. Actually, not like that. Let temp equal num. Temp modulo 10, and then temp will be equal temp divided by 10. So that will be the code to get the numbers. Then we'll do a sort. And we'll do the result by doing vec 0 plus vec 3 minus vec, not minus, but plus. Not even like that. It will be like multiplied by 10 plus vec 3 vec 1 multiplied by 10 plus vec 2. So yeah, this is kind of a formula to sum first with the last and second with the third. So let's, I'm not sure if this needs to be a tuple. I don't think we need any of that because we just sum things. Yeah, we need to make sure temp is also mutable. So this works. That's good news. We've got another possible problem done. Yeah, looks like this time we're first. 0 ms, but we used kind of a lot of memory. Maybe we don't need a vector. Oh, I'm not sure what this guy do. Yeah, it does the same thing as we do. But min pair, max pair, why do you need that? It's way too complex. So yeah, probably this is a little bit of random stuff, why we didn't get fast memory, because extra thing we use is this temp variable, and this is constant. So extra stuff, we use a vector, this stuff. So it will be like n elements were the size of num, but we know that this will be 4 every time. So maybe I can do it like yeah, I can do it like 0 and 4 specifically to start it at 0. But no. Yeah, let's keep it for now. That should be it. I mean, the main logic, it's this formula. And we do it in this following way. As we know that once we sort, if we sum first with the last and the items in between, always first and the last will be smallest. And the middle part will be smallest. So this will be the greedy approach on how to solve it. Cool. This one was interesting. Yeah, let's move on. I think we are done with this page, so that's quite an accomplishment. Let's go page number 2. Sum of values at indices with k set bits. Interesting. Let's see what this is about. K set bits. This is a little bit of intimidating, but we try to understand what do we want to achieve here. So you're given a 0-indexed integer array nums and an integer k. Return an integer that denotes the sum of elements in nums whose corresponding indices have exactly k set bits in their binary representation. What? Okay, so we need to count number of ones in the binary representation. The set bits in an integer are ones present when they're written in binary. For example, the binary representation of 21, it's 10101, which has 3 set bits. So we have 510, 152, K1. Binary representation of the indices. I don't really understand what's nums. Return an integer that denotes the sum of elements in nums. Oh, indices have exactly k set bits. Oh yeah, that's a little bit like it's confusing in itself, because we need to count the number of ones in bits for the indices, not for the values. And then for the indices themselves, once we filter them out, we will do a sum of the values. So indices 1, 2, and 4 have k1. It's nums 1 plus nums 2 and nums 4. Yeah. This is an, I don't know, iterate through this is 1. For each index, count the number of bits by if k is number of results. I mean, that's obvious because that's the problem. So this hint, it's a little bit useless, in my opinion. But anyway, so yeah, I think there is in Rust. I think there is a function, but I forgot. It's called count once. I think, yeah, that's the function. It's called count once. So this function will give us, it's count once called. Yeah, I remember it. So yeah, let's get back to our problem. It's called count once. Okay, so let's code. So we have nums. We need to iterate it. We need to enumerate it. Once we do this, we'll have a filter function which will apply our index and our num. Then we have index. And this is important because I'm not sure if count once it's on usize. But let's try it anyway. Count once as I32 equal k. And then we'll do the folding part. We'll have 0 here. We'll have our mutable accumulator and our item, but our item will be index and item. Here we'll do accumulator plus equal item and return accumulator. So I guess that should be it. Let's try. I'm not sure about this one, if this will work. Yeah, it did work. So actually we can call count once of indexes. So this returns us the number of set bits. So probably this is why this is an easy problem. Yeah, let's check the results. Yeah, let's check the fastest solution. Yeah, this is a counting of bits the old way. So you divide by 2. If it's 1, then you so this is the old approach, and it looks like it's faster than counting bits this way. But anyway, the algorithm is the same, more or less. We do the filtering and then we do the folding part. Maybe we don't need to do that. Anyway, I mean, it's fine, I guess. It's should be good enough. It's good enough for me at this stage. Okay, so let's move on. Minimum number game. Next one. You are given a 0 indexed integer array nums of even length, and there is also an empty array R. Alice and Bob decided to play a game. With every round, Alice and Bob will do one move. The rules of the game are as follows. Every round, first Alice will remove the minimum element from nums, and then Bob does the same. Now, first Bob will append the removed element in the array R, and then Alice does the same. The game continues until nums become empty. Return the resulting array. So this one feels like it uses, or in order to solve this problem, we'll need to know about a special data structure called heap, or min heap in our case. But I'm not sure if this is for exactly needed. Because a min heap, how does it work? First Alice removes 2, and then Bob removes 3. Bob appends 3, and Alice appends 2. So yeah, we can go with the min heap, but maybe it's not necessarily the case needed here. Or is it? We'll need to think. So if we go the other way around, if we just sort it, because complexity-wise it will be exactly the same. It will be like n log n. Worst case for sorting. But should we use a min heap or not? So yeah, let's try to use it anyway. I think why the hell not? It's a good practice, at least for us. So let's create our heap. So it will be a binary heap. I think it's use std collections binary heap. Yeah, I may have a little bit of troubles with the syntaxes. This needs to be mutable. We'll get for each element in nums we'll do heap push. Here it's an interesting point because usually heap will have the max value, but in our case we need a min value. So we need to do it in reversed. So we'll do like reverse and then element. So when we push in reverse, this min, it will transform our binary heap from max binary heap to min binary heap. So this is the logic to create our nums. Now we'll need to get it. And how we'll do that? We'll need to create an array. Let's call it result. I'll have an empty vector, and now we'll do like while heap is empty false. While we have items in our heap, we'll do let Alice pick will be heap pop yeah, let's try like that. Because if you use his here unwrap, we may have troubles. Probably we'll need to write a little bit more code. Let's call it Alice pick. Will be heap dot pop. And then if we have Alice pick, Bob pick, tip dot pop. Okay, so if Alice picked and then Bob picked, and now the Yates will need to check the order. So if Bob has a pick, because here we have like troubles on yeah, and we'll need to, and this will be a reverse stuff. Kind of will need to get I think should be like this. Because we pushed in reverse and we need to get it back from reverse. I'm not sure if this is the correct syntaxes. But let's try anyway. So if Bob has a pick and Alice has a pick, that's an easy scenario. So we'll do like result, push Bob, pick, result, push Alice, pick. But if Bob didn't manage to pick, then we'll have only result, push Alice, pick. And if we don't have it's empty, and we should exit. I guess that should be it. Now, very likely I'll have a bunch of errors. And now we'll need to correct them. So I'm not sure about the syntaxes for this reverse stuff. Yeah, we'll need to include reverse first. I hope it's here. I don't know where it is. No reversing collection. Yeah, let's try to use somewhere here. So it's std compare reverse. So it's in std compare reverse, not here. Std compare reverse. So first stage we got our reverse. Okay, cool. So actually this worked. That's pretty impressive. So we have case 1, case 2. So the min hip worked fine. I'm not sure if we really needed to go with the min hip. Maybe just sorting the array would have been a little bit easier. But I guess we should be fine. Thinking how we can rewrite this to be a little bit more clean. What else can we do? What else can we do? Oh, it's really straightforward. Maybe here to consume it using a fold. I don't know. Yeah, let it be. Let it be. Let's submit it first and let's see if we're right. Oh, awesome. So actually we are the fastest. So fastest solution of the... Ah, no, not us. No, this is not mine. Yeah, this seems very cool. So yeah, I feel like this is a pattern of no, this is not our solution. It's 0 ms of runtime. So why I don't understand why our is first, and when I click on it, it gives another solution. Yeah, this seems a little bit cooler. Rounds imitation and stuff. Yeah. Anyway, I think I like the approach with the binary heap. At least I recalled how this data structure. Maybe it's a little bit of overkill to use it, but fine for now. Cool. We did the minimum number game. Let's go with this one. Decode XORed array. There is a hidden integer array R that consists of n non-negative numbers. It was encoded into another integer array encoded of length n minus 1 such that encoded I equal array of I XOR array of I plus 1. Encoded I equal array of I XOR array I plus 1. For example, if array 1, 0, 2, 1, then encoded 1, 2, 3, you are given the encoded array, you are also given the integer first, that is the first element of R. Return the original array R. It can be provided that the answer exists and it's unique. What? That's interesting. XOR. What does XOR do? So I think like 1 XOR 1 equal 1 or something like that. 1 XOR 0 will be 0. 1 XOR or 0 XOR 1 will be 0, and 0 XOR 0 will be 0. So anything XORed with 0 will give 0, and if we XOR the same number, it will be the same number, I guess. I have no clue. I don't understand how we can XOR with anything other than yeah. First, XOR gate. So 0, 0 is 0, 0, 1 it's 1, 1, 0 it's 1, and 1, 1 it's 0. Oh, so actually it's vice versa. Digital logic gate, or for XOR logical operation, see exclusive OR. Boom, boom, boom. So here will be 0, this will be 0, and the other cases will be 1s. Okay, so we have this. Now let's check and try to understand what the hell do they want from us. It was encoded into another integer. So there is a hidden integer array that consists of n non-negative integers. It was encoded into another integer array encoded of length n minus 1. So what's given? Encoded and first. And what's first? First is 1. You're also given an integer first that is the first element of array. Array 0. Okay. Okay, so yeah, let's get to our drawing board and try to figure it out. What do they want me to understand here? So I'll use my snapshot. Okay, take a screenshot. Let's take this as a screenshot as an example. Let's use a new canvas here. Let's put this somewhere here, I guess. Oh. Okay, just a moment. So we have our encoded array. So let's put this one here. So we have encoded. Once again, what's the formula they want us to write? So encoded of I equal array of y, XOR array I plus 1. So we have encoded of I will be equal array of I XOR array of I plus 1. So we are given the first element. So we know array of first will be 1 in our case. Then encoded of I, which will be 0. Yeah, let's get the first example for us to be clear. So let me use for 0. For 0, we have encoded 1. So here we'll have 1 will be equal array of 0. So array of 0 here. We know the first, it's 1. So we'll have 1 here. XOR array I plus 1. So what stuff will give us 1? Okay, so if, here I'll write the outputting number. So we have 1, which will be first, and then array I plus 1, so 0 plus 1, were the first element. We know that 1 XOR 0 gives 1, so then here we'll have 0. So let me write somewhere here the rules of XOR. So if you have 1 XOR, yeah, maybe it's too big. 1 XOR 1 0, 1 XOR 0, 1, 0 XOR 1, 1, and 0 XOR 0 will be 0. So that's the rule of XOR. But I don't understand what to do with the 2's and stuff. So we assume we got 0 here. Then the next stage we have 2. So let's assume we've got 2 here. Let me use, I guess, this color. So we have 2 will be equal array of I will be 1 in our case, or 0. And we do XOR array of I plus 1. And in this case, it will be 2 here because I will be 1. What gives 0 XOR I guess 0 XOR 2 will give us result 2. Yeah, looks like the logic is correct. 0 XOR 2 will give us 2. Then we put 2 here. We've got the next answer. So last one, which will be 3. And we have 2, the previous, XOR array I plus 1, which will be 3. 2 XOR what gives us 3? How in the world that's 1? How 2 XOR 1 gives 3? I don't understand that. Two XOR 1. What's that? Oh. Yeah. Okay. So there is a function, but now we need to understand the algorithm. So if we put, yeah, we need to understand this algorithm. Works is that when you XOR a character with a space, the character gets uppercase or lowercase, and when you XOR XOR x with x, it returns 0. So when I XOR two characters of two ciphertext, yeah, let's see this. How to XOR two hexa numbers by hand fast? I have an upcoming exam where I can use a simple calculator and some simple question, or where AS round key and no, write it by hand. Okay. XOR table. Okay. So there are tables for XORs like 2, 1. Yeah, you see 3, or 1 XOR 2, it's 3. 1 XOR 2, it's 3. Okay, so we have there is a table for that. But how in the world we need to know this table? Yeah, let's see. So constraints. Yeah, let's see the hints. Since that's encoding, okay, so that's logical. Array I plus 1 will be encoded I XOR array I. But where do we get this encoded XOR array? Yeah, maybe there is a function. I never used it. Maybe there is a function in JavaScript, which, not in JavaScript, in Rust, which does it. Yeah, let's try to see. Rust XOR. Bit XOR self right hand. Okay, so there is a, and is it in Rust? Yeah, it is. Standard version, so it's in bit XOR. And how to use it? Okay. Oh, so we can use this operator. Yeah, let's give it a shot. I just want to do a small test here. I just want to check if this is what we have, what we want actually. So let's create a simple test. Test XOR, I guess, maybe like this. Let me create a simple test, and we have like assert equal to XOR 1 and expect to be free. Looks like I have somewhere here a little bit of bad code. Yeah, we'll need to clean this up first. And then let's run again. Okay, so that's pretty cool. So yeah, I'm not experienced in, let's say, bit operation, bit manipulation in Rust or in other languages, but that's really, really cool. Okay, so they give us the formula. I think what we need to do, just to code it. So what's the formula? Array of I plus 1 will be encoded I XOR array of I. So we have first, let's do mutable result, which will be a vec, and we start with first. Then kind of will need to fold the values. Yeah, I guess the simplest way will be to have a tuple where I use pop, where I use last. I can use pop or last. Okay, so I'm thinking how I can write this a little bit more interesting. Because now we can do encoded that iterator, that fold. Or maybe here we can dig into scan. Because I think scan works as a fold, but it's a better suitable case here. So let's check Rust scan. Because I feel like scan it's better for this. Maybe not. Okay, that will be it. Yeah, an iterator adapter, which like fold holds internal state, but unlike fold produces a new iterator. Scan takes two arguments, an initial value, which seeds the internal state, and a closure with two arguments, the first being a mutable reference to the internal state, and the second an iterator element. The closure can assign to the internal state to share state between iterations. On iteration, the closure will be applied to each element of the iterator and return value from closure. An option is returned by next method. Thus, the closure can return some value to yield value or none to end the iteration. Okay, so let's see an example. So we have scan state x. State will be state multiplied by x. And then we can collect, maybe. Okay, and then we can try that. Yeah. I never use this. I never use this, but let's see. So we'll seed it first here. Then we'll have state, and then we'll have item, coded item. What we need to do is return a sum, which will be the next one. Yeah, and then we'll need to collect the values. Never used scan in my life, so here we may have a little bit of troubles. But hopefully everything will go smoothly. Okay. So we'll need to return next state. So in state will be 1. So I guess state we'll need to make it mutable. Where do we need to make it mutable? Will be encoded of I XOR array of I. So will be it XOR state and some state. Will that work? I have a feeling it will not. Mutable I32. So this, yeah, let's try like that, I guess. Let's try like that. Uh, 0 to 1. Oh, but we missed the first one. And how we can include it? Yeah, that's correct. Collect. Yeah, so we are pretty close, but we miss the first element. And in order to not miss it, let last so be a vec 532. And here we'll do like vec first. I'm not sure if this will work though. Yeah, let's give it a shot. No, this doesn't work. Then we can do maybe like okay, back first. Last, and we use concat. This should work. This is the way on how we can concatenate two vectors. Yeah, so this works. Is it the fast? Yeah, I kind of like this approach, but I missed the way on how we can actually add the first value into the state as well. How can we do that? Yeah, let's submit first and see if this works, because yeah, it does work and it's pretty fast. Yeah, that's simplest way on how you can do it. So we starting 1 plus 1 and do the decoded part. I did it with scan, wanted to learn how to use it. Yeah, I do not see scan anywhere. Yeah, let's ask Google how to keep the first item in Rust scan. Okay, so we do a chain 1 0 chain. Oh, yeah, that's really, really cool. Yeah, that's really, really cool. That's really nice. If I understood it correctly, we can do it a little bit differently. So yeah, that will be very nice if we manage to do. So we'll have this part, yeah, but we'll not need it. So we'll have like iter once first, we'll chain, and then we'll chain this part. And yeah, I need to reformat it. Let me use my stuff somewhere here to have it in a better form. Okay, how about that? So we chain it, but looks like we missed something. Yeah, and that should work. Yeah, looks like we didn't unclose delimiter. Yeah, we kind of missed to close this. Yeah, we kind of need to include that. But where this stuff comes from? Iter. Maybe just try once. Std iter once. So this, so once first, run. Yeah, this looks really good. First. Yeah, this seems like there is a trouble. Yeah. Anyway, I'll make this work. I need to make this work. So what's the problem here? So we expect that because of return type found chain once. Yeah, kind of we need to collect for sure. So we need to collect that. Awesome. So this worked. So we chained two iterators and managed to get the values. So this should be pretty optimized. If this will be first, yeah, still not first. But we don't use anything extra, so I expect like to have low memory. Yeah, this is bugged. It shows me here, but I didn't see my result. I see something different. Yeah, we're online up to 2 hours. I think I'm done for today. We didn't get as many problems as I would like. I think we solved like 4 or 5. But the amount of learning which we did today, it's pretty high. So I really, really like that. We learned about scan first time. And also we recalled how to use a heap, a binary heap. And I think we learned something else, but I forgot already. So yeah, thank you everyone for joining the stream, writing comments. Wish everyone good luck and solve as many problems as you can. This will make you better engineers. Have a nice evening, guys.